Hello, my name is Jamie Pacheco, and today I'll be teaching you about the bucket sort algorithm, a very unique and very cool algorithm for sorting numbers. So, let's get started. Now, as the name implies, bucket sort uses what we call buckets to separate data into smaller subarrays. These buckets can be any data type as long as it implements the list ADT, which is important in storing the numbers into individual categories. Now, these buckets are filled by taking a specific index formula and applying it to each array element. Now, there's two major index calculations or formulas, and I'll go into both of them in more detail in a bit. Now, these buckets, after being inserted array elements, are then sorted individually. You could either recursively call bucket sort onto them, or you could use a more simple sorting algorithm such as insertion sort or bubble sort. Now, these subarrays, when sorted, are then combined and concatenated to create the final sorted array. Now, some of the use cases for bucket sort are primarily meant for uniformly distributed data. So when data points have very low differences and the differences are very close to each other, the efficiency of the algorithm actually expands. So as we can see here, we have a very uniform distributed data, so when it's calculated, it will be done so more efficiently compared to the non-uniform distributed data, as you can see here, where the differences between each data point are very fluctuating. Now, bucket sort can be used with integers and floats, with floats working especially well because of the floating point, which allows for a more distributed sense within the buckets. Now, as I stated, there's multiple ways of calculating the index, and in one particular case, it's very simple if you limit the range of values. So in the case you limit the range of values from 0 to 1, the implementation is very simple. All you have to do is take the element at index I and multiply it by the size of the array. So in the case where you have 10 elements and you have, say, the number to the in the picture to the right, 0.78, times it by 10, so you get 7.8. Then you floor it to an integer and you get index 7. Now this works especially well because when you actually calculate it, because it's between values 0 and 1, they're always going to be within that range. So no matter what it is, it's going to be in that range, which is very efficient. However, it does limit the data that can be used. So you're most likely not going to want to use integers because that would just put them all in one singular bucket, which would just make it completely inefficient. It kind of defeats the purpose of bucket sort. Now, for the more complex index calculations when you need numbers greater than 1.0, the buckets are then assigned range values. These range values are calculated from the greater range between the max element and the min element. So in the case of the list to the right, we have element 11 and we have element 3. So the range then comes out to be 8. And this is important because when divided by the actual size, you get the value 1, which then represents the coverage of each bucket. So each bucket will cover a range of 1.0. So any floating numbers in between or inside that range will be inserted in that bucket. So to calculate each individual element's index within the actual bucket array, you take the element, subtract it from the min element to ensure it's in the range, and then divide it by the range, which will then give you a specific index, which overall is very important because this allows us to use larger numbers and integers, which is very cool. So an example is given these numbers in this array of 10 elements. So because we have 10 elements within this array, we create 10 sub-buckets. These sub-buckets are then iterated through to create a new list inside. These new lists are then taken and values are put inside them. So based on each array element, we have 0.78, and as stated in the simple calculation, taking 0.78 times it by 10 and flooring it to an integer, you receive the value 7. So we know to put this in index 7, and we do this for every subsequent value, which will come out to be being index 7, index 1, index 3, index 2, so forth. So then after all sub-buckets are then filled with values, or their respective values, they're then sorted using whatever auxiliary function you may want to use. So it could be recursion, but in this case it doesn't really matter. So we are then given the sorted arrays in which we concatenate to create the larger sorted array. So some characteristics of bucket sort kind of reveal how unique it is in the sense of its actual implementation of sorting. So the time complexity comes out to be O of n on average and in its best case, which is very good. However, at its worst case, it's O of n squared. This is because at times when you have non-uniform data, all of the data will be stacked into one index. Therefore, it will just basically use the sorting algorithm inside of the auxiliary to basically calculate the sorted array, which at times can be efficient or it cannot be efficient. So it depends. That's why it's good to pick a good auxiliary function. Space complexity ends up being O of n plus k, with n representing the array length and k representing the number of buckets. So bucket sort does tend to be a very memory expensive algorithm, especially for larger values. So because it creates new arrays and then it ends up returning a new array, it ends up being not in place, which is unfortunate in some cases. Now the stability depends on the auxiliary sorting algorithm used. Something like merge sort will be stable, however other sorting algorithms will not be stable, so it really depends. So it is always good to pick a good auxiliary sorting algorithm. Okay, now that we've kind of gone through more of the abstract characteristics of bucket sort, I now want to go to the actual code implementation, just to show you guys the difference between the index calculations and how the simple one compares to the more complex one. So starting off with bucket sort 1, which implements the more simple index calculation, we then start with the actual instantiation of the two-dimensional array that contains our buckets. We then want to create it of size, which in this case is the size of the array or the amount of elements, which is important because you have to match the amount of elements or the amount of buckets to the amount of elements. After we do that, we then iterate through the buckets two-dimensional array to instantiate list objects within each index. After doing that, we then iterate through the array, and then we assign a bucket index based on the array times the size. As stated within the slides, because it's between 0 and 1, it's going to end up being within the range of 0 and the size. So it'll work out in the end. It's very cool, actually. After we calculate the bucket index, we then assign that index here, accessing this list, and then we push the element within that list. And we do that as many times as till the size, and then we continue on, which here is where you would implement your sorting algorithm. Now here, all I did was use the basic sort implementation that comes with lists. However, you can use any sorting algorithm. Here you might want to use recursion and input bucket sort, so you could do bucket sort 1 with the array, or you could do merge sort. You could do whatever sort you want. However, the biggest thing is you want to recognize the implementation and how it might affect efficiency. So now we create a new array on the heap of size to kind of complement the inputted array. We then keep track of the index in order to keep track of where we're going to place the elements within here. And now we iterate through the two-dimensional array, accessing a new bucket each iteration. We then create an iterator for said list. The iterator basically just allows us to access each element very easily and making sure we don't get out of range. So now we access the index of the sorted array based here. We input the actual element, and then we increment the index. This will continue until the bucket is at its end. Once the bucket's at the end, we delete the bucket just to make sure that the actual heap's not overflowing and we're not becoming too inefficient. We then increment through the other buckets and continue until there's no more buckets left, to which we then return the sorted array. So overall, this implementation is not too bad, mainly because the index calculation is very simple. Moving on to the more complex one, you'll notice there's several more components, but breaking it down, it's actually not too complicated. So we first want to grab both the max and min element. This allows us to calculate the range. So say if I said in the slides of examples where you have A through E, then 11 and such. So take for instance here, you have the max element 11, the min element 3, you subtract it, which you would get range, and divide it by size. Size might be 9, 10, but let's say it's 8. The range would be 1, and if it's 9, it would be a float, and so forth. So then, now that we have the range, we can continue on with our calculations. The rest is the same as bucket sort 1, up until we hit here. Now, you'll notice difference. Difference, I didn't really explain that well because it's more of a logical based implementation rather than more abstract, so it's not universally applicable. However, the difference allows us to ensure it does not go out of range, because there's instances in which the difference will calculate to 0, in which at that point it might go out of range. So it's crucial that we ensure that it doesn't. So if difference does equal 0 and the array element does not equal the min element, we then take the bucket and we access the index of array minus min element. This is crucial in ensuring that it's actually within the range of elements, or the size. And then we divide it by range, which then gives us the index. And then we subtract 1. That gives us the proper bucket that we have to insert the element in which we use the pushback method, and then we insert the element. Now, if this condition does not equate to true, then all we have to do is the same thing. However, we do not subtract 1. That's the only difference, because it's not needed, because it's not going out of range. So we increment through all of the elements, and then once we do that, we then sort, which here I just put an extraneous if statement. You don't need it. It does make it slightly more efficient, just reducing the amount of iterations and sorting. So it might help if you use a more complex sorting algorithm as your auxiliary, but in the end, it doesn't really matter that much. And then to continue on, which is very similar to bucket sort 1, we then basically iterate through it and inputting each element into the new sorted array, in which we return at the end. So that is it. Now, this does appear a little more complicated than the other one. So really, bucket sort has like its use cases, and sometimes you may think other sorting algorithms are more useful. How it really depends. So the best thing I could say is to make sure that your data actually requires bucket sort. Floats are very good for bucket sort. If it's 0 to 1, then you're going to want to use bucket sort as well. But for more, simplistic types of data, maybe just pure integers, you might want to look at other ones. So it really depends. But overall, bucket sort is a very unique implementation of sorting, and it does a pretty good job with O of n. So overall, if you think the characteristics appeal to your data set, use it. If not, don't use it. So that is that. Thank you for watching, and have a good day.